What is quantum computing? You've probably heard quantum computing described as the next big leap in technology, but what does that actually mean? To understand it, let's start with something we are all very familiar with: classical computers, our laptops, our phones. They process information using bits, tiny switches that can be either 0 or 1. Every app, video, and spreadsheet ultimately reduces to long strings of these zeros and ones, but quantum computers don't follow the same rules. They rely on qubits, quantum bits, which behave according to the strange laws of quantum mechanics. A qubit isn't just 0 or 1, it can be both at the same time, and this property is called superposition. And it means that instead of a light switch that is either on or off, you have a dimmer switch that can be anywhere in between. And it's not that we simply don't know whether the qubit is 0 or 1, it truly is both. A qubit might be 90% 0, 10% 1, or any other mix. It exists in a kind of blended reality until we measure it. Now add the second crucial ingredient, entanglement. In classical computing, 2 bits can form 4 possible combinations: 0001, 1011, each separate and independent. In quantum mechanics, 2 qubits can exist in a single combined state, say 50% 00, 50% 11, where the two are linked so tightly that if you measure one, you immediately know the other, no matter how far apart they are, and that is entanglement. It's not just that each qubit has its own blend, the entire system is one giant superposition of all possible combinations. Put this together and you get something extraordinary. A classical computer solves problems step by step, checking one possibility at a time. A quantum computer manipulates all the possibilities at once. Think of it as gently nudging an enormous number of potential answers toward the right one simultaneously, instead of testing them one by one. And this parallelism is why quantum computers can in theory solve certain problems far faster than classical ones. So why does it matter? Some problems that would take classical computers longer than the age of the universe could, at least in principle, be solved by quantum computers in hours or days. And this is not just about how fast they can be solved, it's about a different kind of computation. One famous example is cryptography. Most modern online security, everything from bank transactions to private emails, relies on the difficulty of factoring very large numbers. Multiplying 2 big prime numbers is easy, but given only the product, figuring out the original primes is nearly impossible. That hard-to-reverse property is what keeps your passwords, my passwords, our credit cards safe online. Quantum computers can break this system using an algorithm called Shor's algorithm. A sufficiently powerful quantum computer could factor those large numbers exponentially faster than any existing supercomputer. What might take millions of years could in theory take hours. And that is why governments and financial institutions are racing to develop quantum-resistant encryption before large-scale quantum machines arrive. Another powerful application is simulating nature itself. At the smallest scales, the universe is quantum mechanical. Molecules, chemical bonds, and biological reactions all obey quantum laws. Classical computers struggle to model them accurately. They approximate. Quantum computers, by contrast, can simulate the systems directly. And this could transform materials science, energy storage, and drug discovery, allowing us to design molecules with specific properties before ever synthesizing them in a lab. And it is tempting to think quantum computers will make everything faster. They will not. They are not general-purpose upgrades. They are specialized tools, brilliant for certain types of problems, but quite useless for others. Video editing, spreadsheets, gaming, all of that remains firmly in classical territory. Right now, researchers can entangle dozens to hundreds of qubits. To outperform classical machines on meaningful problems, they will likely need thousands, perhaps millions, working together coherently, and that is the challenge. Quantum systems are unbelievably delicate. A stray vibration, cosmic ray, an atom bumping into one qubit can collapse the entire computation, a process called decoherence. Protecting and stabilizing qubits long enough to finish a calculation is one of the hardest engineering problems in science. Hardware is improving rapidly, but the software frontier may be the real bottleneck. We know a handful of algorithms, factoring, certain optimization problems, some physics simulations where quantum speedups are proven or likely, but for most real-world tasks, we simply don't know yet whether a quantum shortcut even exists. And even the much talked about quantum AI probably will not transform machine learning soon, because quantum systems are not naturally suited for messy, unstructured data. The field is moving in steps, new hardware breakthroughs, then new algorithms, then surprising applications no one foresaw. Quantum computing will not replace classical computing. It will complement it, solving problems that classical computers cannot even touch. So when people say quantum computers will change everything, it's not really true, at least not anytime soon. They will change some things, such as cryptography, chemistry, logistics, finance, perhaps entire fields of scientific research, but not everything. The power lies in tackling the impossible problems, not in speeding up the ordinary processes. And that is the real promise and the realistic state of quantum computing. If you lead a company or you are building one, here are a few practical things you can do right now to prepare for the quantum era. First, track where quantum intersects your industry. Even if it feels early, assign someone on your team to monitor quarterly for credible advances, especially in areas like optimization, logistics, cybersecurity, and materials. Second, audit your data security exposure. Ask your CTO or your service provider how long your current encryption standards would hold up if quantum decryption became practical. Start exploring post-quantum cryptography options now. Third, add quantum awareness to your long-term planning. When you review your 3-year or 5-year technology roadmap, include a simple question. If quantum becomes viable sooner than we expect, where could it affect us? What we should pay attention to? And this keeps you prepared. Fourth, partner instead of building from scratch. Don't try to create a quantum program internally. Instead, partner with university labs or platforms. Don't try to create a quantum program internally. It will not make sense for most organizations. And fifth, map where quantum could deliver value. Look at the parts of your business that are complex or compute intensive. Portfolio optimization, scheduling, risk modeling, product design. These are the areas most likely to benefit first. And finally, build a culture of hybrid thinking. Encourage your technical team to understand both quantum principles and classical algorithm design, because the breakthroughs will come most likely from people who can bridge both worlds. Leaders who stay curious and prepare early can leverage advancements instead of being unpleasantly surprised by them. If you found this video helpful, subscribe to the channel, like the video, and share it with leaders and business owners who are interested in AI, automation, technology, because we are specifically covering how you can integrate it into your business and what you need to know. You can also download some free gifts from us, the Breakthrough Decisions Guide with 25 AI prompts, carefully crafted, that can help you with decision making, at firmsconsulting.com/decisions. Your checklist of 5 reasons people ignore leaders. This is about executive presence, communication, and you can get it at firmsconsulting.com/on-the-room. You can also get the key insights and action steps from this video, along with additional resources inside our free community at firmsconsulting.com/action. Thank you for watching. Don't let complexity of tech, AI, automation confuse you. We can figure it out, and I'm looking forward to see you in the next video.